right, good evening, AP Chemistry. Chapter 8, video number 4, bonding, general concepts. We're going to go finish up Lewis structures. We're going to talk about exceptions to the rules, resonance, and calculating and why you calculate the formal charge of a Lewis structure. So first, section 11, exceptions to the octet rule, octet meaning 8. I actually touched on these in the last video. Some typical exceptions to the octet rule. Hydrogen, of course, is a terminal atom. Hydrogen is really never a central atom. Hydrogen will only accommodate 2 electrons around it. It's the only terminal atom that has an exception to the octet rule. Every other terminal atom will achieve an octet. All your exceptions are really centered around the central atom. Boron and beryllium can have less than 8. They can have 8. They can't have more than 8. They can have 6, 4. The elements in period 3 can have more than 8 due to the d orbitals. You never go up beyond 12. C, N, O, and F are really the only ones that obey the octet rule religiously. Carbon, typically 4 bonds. Nitrogen, 3 bonds, a lone pair. Oxygen, 2 bonds, 2 lone pairs. Fluorine, 1 bond, 3 lone pairs. Resonance and formal charge. Resonance is not the same as isomers. Isomers are organic compounds with a group attached at different carbons. Resonants are not the same as isomers. Isomers are traditionally organic compounds with a functional group attached at a different spot. Isomers will usually have the same number of atoms, the same type of atoms. It's just that the functional group, which this is an alcohol, the functional group is at a different spot on the chain of carbons. Notice on the left, the functional group is on the third, and on the right it's on the middle one. One's iso and one's not. Isomers are completely different properties, completely different substances. So do not mistake resonance with isomers. Resonance will usually revolve around a double or triple bond in a molecule that is 3 or more atoms in the structure. Resonance, more than one valid Lewis structure can be drawn for a given molecule. And that Lewis structure will contain a double or triple bond, and that Lewis structure must be 3 or more atoms in the structure. Data shows that when a double bond exists, it does not alter the length of the bond, even though it should. Single bonds, double bonds, triple bonds, those are the only type of bonds that exist. A single bond is the longest of the 3. A double bond is shorter and stronger than a single bond, and a triple bond is the shortest and the stronger of the other 2. A double bond existing in a molecule with 3 or more atoms, you would think that data would show the double bond to be shorter than the single bond, and it doesn't. It actually shows that the bond lengths are all the same. And the explanation is that that double bond moves. The electrons that make up that double bond are delocalized and can actually move around the structure. And the bond lengths are measured as averages. So here's a quick example. All right, so here are 3 examples of resonant structures. Notice that they are at least 3 atoms in each structure. Also notice that each one of them has a double bond in some way, shape, or form. That means I came up short on the central atom and I had to have a pair of delocalized electrons swoop in and make a double bond. SO2 is the first one. Notice that my double bond is on the left side in the first structure and on the right side in the second structure. Both structures are valid. Both have 18 electrons. The oxygen, the sulfur, and the other oxygen all achieve an octet rule. There is nothing wrong with either structure based on the rules. Ozone. Ozone is 3 oxygens. I have 2 structures there for ozone. Both of them achieve the rules. I have 18 electrons. The oxygen, each oxygen has 8 around it. Even though it's a double bond, like here, this is a double bond, 1 localized pair of electrons and 1 delocalized pair of electrons. The oxygen doesn't care. All it wants is 8 electrons around it, and it has it. Carbon dioxide is another example of resonance. When you come up short on the carbon, you could create double bonds or a triple bond and a single bond. So each one of these structures is fine. Each one has 16. Each structure achieves the octet rule for the oxygen, the carbon, and the oxygen, the other oxygen. So resonance usually revolves around 3 or more atoms in the structure and a double bond or triple. There are only 2 examples of an odd number of electrons. Again, the first rule of Lewis structure is to tally up, sum up, the number of valence electrons. If you tally up nitrogen oxide, you get an odd number. Nitrogen's in family number 5, oxygen's in family number 6. That's 11 electrons. This is not a charged entity. You come up with 11 electrons. It is an odd number. The same for nitrogen dioxide. You tally up these electrons, you get 17. These are the only 2 examples where there is an odd number of electrons. Notice they both contain nitrogen. And when you draw the structures, there's a single, unpaired, single electron on the nitrogen. These are the only 2 examples. Formal charge. What is it? It's used for those molecules that can exceed the octet rule. It's used to determine if those molecules or structures are valid. Notice not right or wrong, just reasonable and or valid. Formal charge calculation. It is the number of valence electrons on a free neutral atom minus the sum of the number of lone electrons plus half the bonded electrons. Actually what it comes out to be is that formal charge will be equal to the family number of the atom minus the number of dots plus the number of lines, which I'm going to do an example in a minute or 2. So wait, and we'll do some in class too. It's real easy. Alright, so you calculate formal charge of each atom in the molecule, and you got to determine what's best. Atoms in the molecules try to achieve formal charges as close to 0 as possible. Any negative formal charge is expected to reside on the most electronegative atom. Alright, so here's an example. Alright, these are 2 perfectly valid Lewis structures for the sulfate ion. Notice they are in brackets like all ions will be. I have 32 electrons in both structures. The double bonds in the right structure are fine because sulfur is in the third period on the periodic table. Therefore, it has that empty D, so it can perfectly accommodate an octet rule. There is nothing wrong with either structure. But if a challenge was placed down, we would have to calculate the formal charge of the oxygens and the sulfur in each structure and see if one of them is more valid than the other. All right, so again, this number right here, this is the family number. This is the number of valence electrons the standalone atom would have, minus this guy right here. This is the number of lone electrons, the unbonded, the dots. You count each dot around the particular atom. This number here is the bonded electrons divided by 2, 1/2 the bonded. So this is technically going to be the number of lines, because bonded electrons means you count the number of electrons around the particular atom and divide by 2, so it's number of lines. And then you just do a real simple math problem, and you compare this row here to this row here. Notice that in all honesty, sulfur is a highly electronegative atom. This structure on the right is probably going to be more valid. This one's going to be more valid because of that +2. Sulfur is electronegative, so this is a more valid structure. Let's do another example, simpler one. Alright, so here's another example of carbon dioxide. Oxygen, this guy on the left. Family number, number of valence electrons of the standalone atom, 6, minus lone electrons. There's 4 dots around this oxygen, so 4, plus half the bonded, 2, 4. There's 4 electrons bonded on the oxygen. Half of that is 2. The central carbon on this left structure, the valence electrons, or the family number of carbon, is 4, minus the number of dots, or the lone electrons around the carbon. There are no dots around this central carbon, so 0, plus half the bonded, 1, 2, 3, 4, 5, 6, 7, 8. There are 8 electrons bonded around that central carbon. Half of that, 4. Add them up, 0. Oxygen on the right. Valence electrons or family numbers of this standalone oxygen, 6. 6 minus the number of lone electrons around this oxygen, the number of dots, 1, 2, 3, 4. 4. Plus half the bonded ones, 1, 2, 3, 4. There are 4 bonded electrons on this oxygen. Half of that is 2. So you add them up, you get zeros. Do the same thing for the structure on the right. The structure on the right is not valid. Why? Because oxygen is very electronegative and should not have a +1 formal charge. So this guy is the more valid structure. You will notice I'm not saying right or wrong, I'm just saying it's more valid. And it's more valid based on formal charge.